Question 3 gives us a break from proving identities and instead gives us an opportunity to solve again. Now, these solving questions are a little bit different because you need to use identities in order to solve them. So if we look at A, 2 sine x equals 3 plus 2 cosecant x, one of the problems in this equation is that we don't have the same trig function. We've seen this before on our quiz review and even on the quiz that you wrote yesterday, that sometimes you get an equation that has two different trig functions. The one that you had on your quiz had like a sine squared plus 3 cos x, blah, blah, blah. And you had to use an identity to substitute that sine squared for 1 minus cos squared so that your function all had the same trig function. We're going to do the same thing here. We're going to look at this equation and say, is there a way that I can write this equation using only sine? Because right now I have sine and I have cosecant. Well, what could I change cosecant to? I could change cosecant to 1 over sine. And then this equation would all be in sine. Now, I haven't written it yet because I want you to think, how would you change that 2 cosecant x if you had to change the cosecant to 1 over sine? Because this is the dilemma you're going to have when you come across this question in the test. Should I change 2 cosecant x to 1 over 2 sine x, or should I change 2 cosecant x to 2 over sine x? What should I do with that 2? Should the 2 go down to the bottom of the fraction because I'm doing the reciprocal and it's touching the cosecant, so it should touch the sine? Or should the 2 stay on the top of the fraction and not go to the bottom of the fraction? How do I determine which one it is? And maybe right now you're saying to yourself, yeah, I can see myself having this dilemma on the test. I'm not sure, I'm not super confident which of those two I would go with. So sometimes when we're not super confident, we sort of take it step by step. We say, well, what do I know? I know that cosecant is 1 over sine x. So I know that cosecant x is 1 over sine x. So instead, I'll just start with that. I'll just, one step at a time, I know that cosecant is 1 over sine x. And now I have to do another step. Well, how do I multiply 2 times 1 over sine x? And maybe now I even have another dilemma. Maybe I should multiply the 2, distribute it, and maybe it should be this. Oh my goodness, what should I do? Well, one step at a time, how do I multiply 2 times 1 over sine x? How do I multiply fractions? Well, fractions, you multiply the numerators together, you multiply the denominators together. But with my number out in front, I don't have a denominator, at least not written. Could I write 2 as a fraction? Yes, I could write 2 as 2 over 1. And then if I multiply my numerators together and multiply my denominators together, what do I find? There's the one that's correct. So again, sometimes when we try to just do something directly, we might write down something wrong or we might confuse ourselves. So go back to the basics. Do one step at a time. Look at what we know. We know cosecant's 1 over sine. And then how do I figure out that I'm going to change that 2 cosecant x to 2 over sine x? Well, now I know that that's the right value to choose. That 2 does not move to the bottom of the fraction. All right, I'm going to erase this off to the side. This is the equation that we have. One thing that happens in math, we just did one step to change everything to sine. We get a new step, and now we have to be able to recognize what kind of equation this is and what were our techniques for solving this kind of equation. This is like in grade 11 when you had questions like this with x's in fractions. These were called rational equations. How did we solve our rational equations in grade 11? Well, we didn't like having that fraction. So we asked ourselves, how could I get rid of that fraction? What's the opposite of dividing by x? Multiplying by x. And if I multiply by x, that would get rid of that x on the bottom. But equation rules say, well, whatever you do to one side of your equation, if I want to multiply one side of my equation by x, I have to multiply the other side of the equation by x as well. In order to keep our equation balanced, what you do to one side of your equation, you have to do to the other side of your equation. So in this question right here, I have a sine x on the bottom. I'm going to want to multiply this side by sine x, so I have to multiply this side by sine x. If I do that, the left-hand side becomes 2 sine squared x. My right-hand side, well, if I'm multiplying that whole side by sine x, it's going to get distributed. That would multiply your 3 by sine x, and it would multiply this by sine x, which is nice because then your sines would cancel out, and we no longer have a rational equation. Whew. But now what do we have? Yeah, we have something, it's an equation we've solved before. It's a quadratic equation. It has sine squared. So now we have to say, well, I solved lots of quadratic equations. What do I do with quadratic equations when I want to solve them? I want to factor. I have to make one side equal to 0. So we'll do that. We'll move the 3 sine x over and the 2 over to make one side equal to 0. And now we can factor this. And factoring this one is a fairly easy one to factor. Because it starts with 2 sine squared, that means our only option is 2 sine and sine. Now, our last number is a 2. So that means we either have to go 2 and 1 or 1 and 2. And in this case, it makes a difference. It makes a difference if you put 2 and 1 or 1 and 2. So if you don't know which one to do, if you can't see right away which one to do, then try one of the two and check it to see if it works or not. So just randomly pick 1 and 2 or 2 and 1. Callan, randomly pick 1, 2, 2, 1. 2, 1. So if we picked 2 and 1, we're going to have to check, does our outside and our inside ever make 3? My outside is going to be 2 sine x. My inside is going to be 2 sine x. Does 2 plus 2 or 2 minus 2 ever equal 3? No. So we find out right away that it can't be 2 and 1. So then we're going to check instead 1 and 2. If I put 1 and 2, my outside is 4 sine x. My inside is 1 sine x. Can I ever add or subtract 4 and 1 to make 3? Yes. And I need to get a negative 3, so I'll want my outside to be negative 4 sine x and my inside to be plus 1 sine x. And sure enough, that works out. So again, after you factor, you should always be checking to see what you have works with the line above it. We can now split it up right here. On the left-hand side of this, we'd say that sine x is equal to negative 1/2. On the right side, this factor, sine x is equal to 2. This would be a non-calculator question because 1/2, it's on our pie plate. What family? Pi over 6, pi over 3, pi over 4? Pi over 6. And because sine is negative, you would take your pi over 6 family member in quadrant 3 and your pi over 6 family member in quadrant 4. Sine x equals 2, not on our pie plate. How come this is non-calculator? How can we solve that without our calculator? We can just say it's not possible. Because if sine is opposite over hypotenuse, and you have 2, which would be 2 over 1, can you have a right angle triangle where the opposite side is 2 and the hypotenuse is 1? No. And so we've solved this. And at this point, you might get really excited to go on to the next question, especially on a quiz or test because you're feeling like time is sensitive. Without looking down at your textbook, did we solve this over the correct domain? Do you remember the domain that was given at the beginning of the question? Of course not. Nobody remembers that while they're working on, like, you just start working, right? And you get going. And you're like, oh. So always check your domain after, right? In this case, we're lucky because our domain is between 0 and 2 pi. 2 pi wasn't included, but that didn't affect our answer. That's just once around the circle. That's exactly what we did. We're fine. We've solved this correctly. Now, reflect on this question, because this question involved identities to start it off. But then it connected to 3 main concepts from grade 10 and grade 11 after that fact. First of all, as soon as we used our identity, we got a rational equation. So it's expected in grade 12 that you are experts in solving rational equations in all their forms and how to do that. Okay? After remembering that, oh yeah, with rational equations, we like to get rid of the fraction by multiplying. I've done that by multiplying by both sides by sine x. I get this next step, a quadratic equation. So now you're in grade 12, you're expected to remember how to solve quadratic equations in all their forms. Well, how do we solve quadratic equations? We make it equal to 0 and either factor or use our quadratic formula. This one, you could factor. Well, how do you factor? You've got to remember all your factoring skills from grade 10. And having gone through all of that mental things, going all the way through and then solving this equation, so now you have to use your unit circle, so another concept that comes into play, and get our answers. We still have to remember we should check the domain that this question was. Okay? So this is 3 years of work that you got to being able to solve this question. Because you first of all have to become experts in things that you did in grade 10 and 11. And you have to be able to recognize when those appear inside of a question. And then you also had to be able to do your unit circle really well to recognize the values, to be able to answer that. And it all started with just changing the equation with an identity so you had one trig function in the question. Part B, sine x equals cos x. Again, at first, this is a different type of equation because we don't have a single trig function. And we're going to look at 2 different ways that we can solve this one. Okay? Method number 1, maybe you can just tell from your unit circle. Sine x is your y-coordinate. Cos x is your x-coordinate. Are they ever the same? When? Pi over 4. Good. Anywhere else? Yes, at pi over 4, they're both root 2 over 2, root 2 over 2. Does it ever happen again that they're both the same? Yeah, quadrant 3, right? In quadrant 3, they're both negative root 2 over 2. So then you would get 5 pi over 4. And you're done. You've solved this question between 0 and 2 pi, we would be done. That seems relatively simple, but you really have to know your pi plate and recognize that. This one can also be done by getting things to a single trig function. To get this to a single trig function, the number 1 temptation to use is say, I wonder, I don't have sine squared and I don't have cos squared, but if sine squared plus cos squared equals 1, is sine x plus cos x equal to 1 if I square root both sides? Does that work? Yes? No? Good? Bad? Can you see yourself tempted to use that? Okay? Because you're going to have, oh, if sine squared is 1 minus cos squared, is sine 1 minus cos? Can I do that? The answer is a big no. Okay, this is bad. Okay? Why is it bad? Well, check with numbers. I know that 3 squared plus 4 squared equals 5 squared. Is 3 plus 4 5? No. That's bad. So this doesn't work. So we're not allowed to just change cos x to 1 minus sine x. But in this case, if I would divide both sides by cos, both sides of this equation divided by cos, I get this equation. How can that help me write this as a single trig function? You can make it into tan. Nice. And is tan ever 1 on your unit circle? Yes. What family is tan equal to 1 on your unit circle? Pi over 4 family. And tan is positive also in quadrant 3. Oh. Same answers as we got from before. So that's sometimes nice because I find when they're both positive, it's fairly easy to figure out when they're the same. But sometimes you get ones where it's like negative sine x equals cos x, and then trying to figure out when that all happens might be easier to change it to tan. Okay, we're going to take 10 minutes, 5-10 minutes to work on number 10. Do 10a first, then 10d, because 10d has something in it that a lot of people make mistakes in. So I want you to try it on your own. See if you get the same answers as the answer key, and if you're not, you're probably making a common mistake, so then call me over.